Well, as pretty as the three-dimensional graphs are, they're very hard to think about because we need to process a lot of information in our brain. So it is much easier if we focus on two-dimensional graph where we understand how the utility function corresponds to different utility maps. And this is why that in many cases we'll simply work with this top-down view of a preference map where higher indifference curves represents higher utility levels. It also represents bundles that are more preferable comparing to bundles that sits on lower indifference curves towards the bottom left. So now let's turn to look at a particular indifference curve. Hopefully by now you're comfortable thinking about an indifference curve that is always downward sloping and represents a series of different consumption bundles that are indifferent to a particular consumer. Now, a different way to think about indifference curve is the following. Let's consider the following thought experiment, where we'll first present a particular consumption bundle F to this particular consumer. And then we start to make changes to this consumption bundle in such a way that keeps this consumer just as happy. Not any happier, not any less happy, but exactly as happy. In other words, we're going to make changes to the consumption bundle such that the consumer remains indifferent. So how do we do that? Well, what we can do is we can just travel down this indifference curve. But what does that mean? Well, it means we're effectively replacing burritos in this consumption bundle F by adding more pizzas. So by taking some burritos away from this consumer, while compensating them using pizzas, we can keep this consumer just indifferent. However, we have to be really careful in how we replace these two products with each other. We have to keep the rate of substitution in such a particular precise way so that this consumer isn't made any happier or any less happy when we make the change. And this particular rate is the notion of marginal rate of substitution. Although the notion is a mouthful, this intuition is captured by the indifference curve, which is just the slope of the indifference curve itself. Because think about it, the notion of slope tells us exactly what is the change in y when we change x by 1 unit, while staying on this particular curve itself. That's exactly what we want to do. We want to increase a certain amount of Q1, and what we care about is how much of Q2 can we take away so that we remain along the same indifference curve. As it turns out, this notion of marginal rate of substitution plays a critical role in understanding the consumer's consumption choice. We'll make this notion more precise later on. Therefore, it is really important for us to have a deep understanding of this concept about the way it is defined, the way it is calculated, and the way it is interpreted. Specifically, the technical definition of the marginal rate of substitution can be defined using the utility function and the utility function alone. Well, that's not really surprising because the utility function represents the entire utility hill, which in turn carries all these contour curves that represents all the indifference curves. So of course, all the information of the indifference curves, including slope, are all contained in the utility function itself. The question is really just how to extract that information. We're going to first present the technical definition itself, and then we're going to show how this technical definition corresponds with our previous intuition. We're going to use this notation of MRS to refer to marginal rate of substitution. And the subscripts 1, 2 represents the order of these two goods. In particular, in this case, we're replacing good 2 with good 1. And the question we're asking is precisely that as I give this consumer 1 extra unit of good 1, how many units of good 2 can I take away from them so that they would remain indifferent? In other words, the first part of this equation is simply the conceptual definition we presented on the previous graph, which is exactly the slope of the indifference curve. But it turns out this particular derivative, or the slope of the indifference curve, can be rewritten in terms of the utility function. And the way it will become is this following expression, which is equal to a negative sign, of course, because the indifference curves are downward sloping. But it turns out the absolute value of the slope is equal to the marginal utility of good 1 divided by the marginal utility of good 2. And using the notations we already have in place for marginal utility, we're simply going to write it as marginal utility of good 1 divided by marginal utility of good 2 with a negative sign in front. And we'll frequently use both the notation of MRS and this expression of U1 divided by U2. A couple of notes about this particular expression. First of all, you might ask, well, why do you write marginal rate of substitution as 1, 2 instead of 2, 1? Is there anything specific about this? Is there a right way or wrong way to do this? Not really. They're all equivalent, but the way we're writing it like this is to correspond with the graphs that I've drawn consistently so far, where we have put Q1 in the horizontal axis and put Q2 on the vertical axis. In that case, the slope is more intuitively thought of as 1 unit increase in Q1 and then the corresponding amount of changes we incur on Q2. And this is why we're writing the marginal rate of substitution in this particular way. You can certainly write MRS in a different way, and you will realize that all it affects is the interpretation of this expression, and the particular order really doesn't matter too much when we come to later problems. So again, the interpretation of this expression is that if we increase the quantity of good 1 slightly, how much of the quantity of good 2 can we take away in order to keep the consumer indifferent? And that change in quantity of good 2 is measured by the marginal rate of substitution. So next, we're going to take some hard work to understand how come the slope of an indifference curve that is intuitively defined as this particular expression can be written in terms of utility function as a ratio of the marginal utilities. Before we look at the math, I would want to make it very precise about what exactly are we trying to measure with marginal rate of substitution. So the story we have is that we're traveling along a particular indifference curve, and we're replacing one good by the other while staying along the curve. By traveling along an indifference curve, what we're doing in terms of the utility function is that we're dialing up Q1 while simultaneously dialing down Q2 in an appropriate manner such that before and after the change, the utility function keeps feeding back exactly the same height on the utility hill. In other words, before and after the change or tweaking in Q1 and Q2, the utility function always kick out an exactly same reading. Although we don't know exactly how much this reading is, but because we're traveling along an indifference curve, we do know that this reading has not changed. The altitude of this contour curve has not changed. The height along the utility hill has not changed. And let's call this value U bar, which suggests this is just a constant. The bar above U simply reminds us that this is not a function anymore, but instead just a particular reading that we're locking in. For instance, you might have 2 pizzas and 10 burritos. That gives you a utility reading of 10 units. Now, how do we travel along the indifference curve that represents 10 units of utility? Well, we're going to throw in 1 extra unit of pizza and probably take away a certain amount of burritos. And what we're trying to do is to exactly keep the utility function at exactly the level of 10 units. And that's exactly what we're trying to do. It's just that instead of writing 10 down, we're going to say it is just any fixed level of U bar. In fact, throughout this class, whenever you see a bar above a notation, it usually means a particular constant that we're locking down. Now, once we have this idea fixed, it becomes a little bit easier for us to think about the math we're trying to do. Another way to put this is we're just trying to tweak Q1 and Q2. And we're trying to figure out how Q2 can drop by the appropriate amount such that when we dial up Q1, U will remain constant at U bar. Now please keep that idea in your mind, and we'll look at the math now. So starting from any particular fixed indifference curve, the definition of an indifference curve is that any combination of Q1 and Q2 going through the utility function would give me an exactly the same reading. Now, with the ideas on the previous slide fixed, hopefully it is now reasonably easy to see that an indifference curve is in fact just a combination of coordinates of Q1 and Q2 such that the utility function measured on all such points will give a constant reading of U bar. So what we're trying to do now is to travel along the indifference curve without changing the utility reading of U bar. And the way we're changing it is by dialing up Q1 while allowing Q2 to change with it, but not to change by any arbitrary amount. Q2 has to change in a very particular way such that the value of the utility function remains unchanged, so that we can stay along the indifference curve. And this is why now we're writing explicitly for Q2 to be a function of Q1, to remind ourselves as we change Q1, we're allowing Q2 to change with it. And we would also remember that this constant of U bar will not change, because that's what we're trying to do by traveling along the indifference curve. Now, we would want to introduce a change. We would want to start from a particular Q1 level and now throw in one extra unit of Q1. And we're going to allow Q2 to change accordingly such that U bar does not change. So how is that reflected in algebra? Well, we will take a derivative of this function with respect to Q1. And that's exactly what we do. We dial up Q1 by a little bit and let the function react. As we take derivative of U bar on the left-hand side with respect to Q1, the derivative should be 0, because that's exactly what we're trying to do. We require the derivative to be 0 in order to stay along the same indifference curve. Mathematically, because we defined U bar to be a constant, so taking derivative of a constant with respect to Q1 is 0. But the reason we defined it that way is because we want to travel along an indifference curve. So it is the economics that drives the way we define the mathematical terms here, which in turn drives the result of that derivative. On the right-hand side, we're taking a derivative of the utility function with respect to Q1. But now, just like when we did comparative statics, when we change Q1, there are two channels that are simultaneously affecting the value of the utility function. The first channel is a direct impact coming from Q1. Fixing Q2, as I have a higher Q1, I get more of good 1, the utility value is bound to go up. And that is our first derivative, which is just marginal utility of good 1. However, Q1 in this scenario also changes the utility function through a second channel, and that is by the change of Q2. Well, the reason it's going through this channel is because we're allowing it to deliberately do this, so that by giving this consumer a certain amount of good 1, we're taking away a corresponding amount of good 2. So as Q1 increases, we're allowing Q2 to respond as a function of good 1. And as a result of changing good 2, the utility function then varies. Now, the total effect on the utility function is actually the compound of these two separate channels. One way to think about it is the following. The first effect is a direct effect coming from good 1. When I get more good 1, but fixing the amount of good 2 I have, my utility is going to go up. However, in order to keep my utility level constant, we're going to take away certain units of good 2 away from me. And when you take away good 2 from me, holding the amount of good 1 constant, my utility is going to go down. And how much is that decrease in utility can be moderated and controlled by the specific amount of Q2 you take away when you give me 1 extra unit of good 1. And when you choose this amount very carefully, you're able to have exactly the same effect through the second channel as the first one by having exactly the opposite signs. So the gains in the utility coming from the extra unit of good 1 is exactly offset by the loss of the appropriate amount of good 2 you take away from me. Coming back to this graph here, if I simply give the consumer a little bit of extra good 1 coming from bundle F, the consumer's utility is going to be higher. So how do we maintain the same utility level so that the consumer is indifferent? Well, we have to take away the corresponding amount of good 2. Taking away too little, the consumer will be better off than before. Taking away too much, the consumer will be worse off than before. But taking away just the appropriate amount, then the increase in the utility level coming from the extra gains in Q1 can be exactly offset by the loss of utility coming from the loss in terms of good 2. And that's exactly the idea of the math. Once you understand this particular expression, the technical definition of marginal rate of substitution simply follows from it. Because the left-hand side of this equation is 0, and the unknown factor we're really trying to figure out is what is the appropriate amount of good 2 we should take away when you give me a little bit of extra good 1. Therefore, this is our big unknown here. And what we're trying to figure out is just what is this expression in terms of everything else we already have. But now, notice that this expression is just marginal utility of good 1, and this expression is simply the marginal utility of good 2. So we can simply subtract this amount on both sides of this equation, and then divide by this quantity, and then we're all set. That is precisely this expression we have in our definition, which is exactly minus marginal utility of good 1 over marginal utility of good 2. And there we go. Now, after the hard work, we have shown that we can calculate marginal rate of substitution in terms of marginal utilities of two products. So now let's put this operation definition to work. Let's take a particular Cobb-Douglas utility function with a parameter alpha taking the value of 0.3. As a result, the value 1 minus alpha is going to be 0.7. And then we have a utility function that looks like the following. So with this utility function, let's try to calculate the marginal rate of substitution. This is our first time encountering this problem. We don't know what to do, and all we have are the definitions. So let's make good use of them. First of all, we know that to calculate marginal rate of substitution, we can simply calculate the marginal utilities of the two goods respectively, and then take a ratio of them and take the negative value of that outcome. We're going to break down this process into two steps. In the first step, we're going to calculate the marginal utility of each product respectively. And then we're going to just take the ratio by plugging them into the definition of MRS. Now let's get to it. To calculate marginal utility of this utility function with respect to good 1, it is very similar to the previous practice we've done with a very similar Cobb-Douglas utility function. But what we did previously was with the alpha value of 0.5. So now, with a slight change of values, can you try this? What do you have? Well, to calculate the marginal utility of product 1, we're going to take a derivative of the utility function with respect to the quantity of good 1, while holding the quantity of product 2 constant. In other words, we're asking if the consumer has the same amount of good 2, but now has a little bit more of good 1, how would the level of utility change for them? Now let's take this calculation. Because we're taking a derivative of this utility function with respect to Q1, while holding Q2 constant, we're going to treat Q2 to the power of 0.7 as a constant, which comes out of the derivative. And we're going to treat Q1 as a variable that is changing. Again, if you're not comfortable with the notations yet, just treat Q1 as x and Q2 as a constant. So instead of taking derivative with respect to Q1, which you may still not be familiar with yet, let's try to replace it with the placeholder of x, a trick that we've used before. Now, if I take a derivative of a particular function that is x raised to the power of 0.3 times Q2 raised to the power of 0.7, and I'm going to take derivative of this function with respect to x, what do we have? Well, the constant that is not changing with x, which is Q2 raised to the power of 0.7, is going to come out of the derivative. And what we're left with is just taking derivative of x raised to the power of 0.3 with respect to x. And now all we have is just the power rule. We're going to take the power of 0.3 down as a multiplier, and then the power on x will decrease by 1. Now we have Q2 to the power of 0.3 times 0.3 times x to the power of minus 0.7. And that's it. That is our result of the calculation. Of course, you need to recognize that x is just a placeholder for Q1, so make sure when we return to the economics, swap out x back into Q1. Now, once you have this expression, the problem is essentially done. But again, if you're being more obsessive about it, we can rewrite it in a slightly prettier form. And to do that, we just need to recognize that Q1 raised to the power of negative 0.7 is simply 1 over Q1 raised to the power of 0.7, exactly like our previous example. And now you can collect Q2 over Q1 because they share the same power. And now you can just raise the entire ratio by the power of 0.7. And that is our result. The calculation of marginal utility of good 2 is very similar. Can you try that on your own? Well, when we take derivative with respect to Q2, we will treat any function of Q1 as a constant. So for similar reasons, we're going to take out Q1 to the power of 0.3 as a coefficient, and then take derivative of 0.2 to the power of 0.7 with respect to Q2. And of course, the result is the power 0.7 comes down as a coefficient, and the power on Q2 drops by 1 down to minus 0.3. And then similarly, we can rewrite it into this ratio form between Q1 and Q2. Now, with the marginal products calculated, we can just plug them into our definition of marginal rate of substitution. Remember that in previous slide, we've defined and derived this particular formula that says marginal rate of substitution, which is the slope of the indifference curve, is equal to minus the ratio of marginal utility of good 1 over marginal utility of good 2. Of course, this is when we're referring to the slope of the indifference curve where Q1 is on the horizontal axis and Q2 is on the vertical axis. If you would have plotted it differently, then the slope would be the inverse of what we're representing here. So instead of having U1 over U2, you'll have U2 over U1. Now back to the calculation. In this particular case, as long as we're sticking with Q1 on the horizontal axis in our mind, the marginal rate of substitution would be exactly this expression, where we simply plugged in the value of U1 and U2 that we have calculated into these positions. And now we can try to simplify this expression slightly, because if you can recognize, we have a very similar looking object both on the top and the bottom of this ratio. They're very similar, but not exactly the same as each other. But they would be once we take the reciprocal of one of them. There are at least two ways to see how the algebra goes forward from here. We're going to talk about the first way. Well, the first way is simply to distribute the powers into the ratios and then write them accordingly. So what we'll have is we'll have 0.3 on the numerator and 0.7 on the denominator. While similarly, we'll have Q2 to the power of 0.7 on the numerator, but it's divided by Q1 raised to the power of 0.7. Therefore, that part is going to be on the denominator. What about the bottom part? Well, we're dividing 1 on top by this ratio. So, in fact, 1 divided by Q1 divided by Q2 to the power of 0.3 is simply Q2 divided by Q1 raised to the power of 0.3. And that will give us Q2 to the power of 0.3 on the top and Q1 to the power of 0.3 on the bottom. Now what you realize is that we can collect these terms now because they're both functions of Q2 raised to some power. We can simply add up their power. And that will give us, coincidentally, a power of 1. In fact, the expression simplifies dramatically to 0.3 times Q2 over 0.7 times Q1, which of course is just 3 over 7 times Q2 over Q1. Another way to see how the calculation goes is to simply use these expressions without simplifying them. If we plug in these two expressions into U1 and U2, you would have very similar expressions. And by very similar means of collecting similar terms, you would have gotten exactly the same expression. If you're more comfortable with the second approach, feel free to do that. All this algebra does not carry any interpretations in terms of economics per se. So we really don't care which way you get there. But one way or another, it is the algebra and the mathematics that help us think through these hard problems to get to a very neat and clean answer at the end. Now, having calculated the marginal rate of substitution for this particular Cobb-Douglas utility function when alpha is a special value of 0.3, let's take a look at the general version of Cobb-Douglas utility function, where we do not impose a particular numerical value for the parameter alpha. The question is the following. Given that we're now familiar with the way we use to calculate marginal rate of substitution, can we derive a more general result for the general Cobb-Douglas utility function in terms of marginal rate of substitution? Do they all share a similar format? Let's try that now. Again, to follow the same two-step approach that breaks down the problem, we're going to calculate the marginal utility of good 1 and good 2 respectively, and then plug them into the definition of MRS, which will give us the answer. To calculate the marginal utility of good 1, again, we take derivative of the utility function now with an abstract parameter of alpha with respect to Q1. However, we simply need to remember that alpha is just some fixed number, just like 0.3 we worked with, and the 0.5 that we have worked with previously. So now, by very similar means, alpha simply comes down off Q1, and the power on Q1 drops down by 1. We cannot simplify the expression any further, although you might choose to rewrite it differently in the form of a ratio. This is really a matter of personal preference, so it is entirely up to you where to stop. Similarly, we can calculate marginal utility of good 2. Now, that will look slightly different because the power on Q2 is 1 minus alpha, not alpha. So So the power that comes down is going to be 1 minus alpha. And when Q2's power decreases by 1, it's going to become minus alpha, as opposed to alpha minus 1. And now we have the separate expressions for U1 and U2, or you can use these expressions to proceed as well. And we will just move into step 2 by plugging in these two marginal utilities into the operating definition of MRS. We're going to take a ratio of the marginal utilities and put on an active sign. By a very similar calculation, which is exactly the same as the previous slide, with the only change to be that we're not imposing alpha to take a particular value, we will arrive at exactly the same expression. In the first step, we're simply plugging in these expressions. In the second step, we're simply trying to arrange them in a way that allows us to collect the terms. You can think of the same distributing power operation we've done on the previous example, or you can think of it as flipping this term from the bottom to the top by also reversing the order of the ratio within the bracket on the bottom. Now, let me demonstrate some details about how this particular step of algebra can be done if you're confused by the details. If you're comfortable with these calculations, just skip forward a little bit and we'll get back to the economics part. So, to see the algebra that comes from this step to this step, the key challenge in the algebra that goes from this step to the next step is how do we deal with this particular ratio on the bottom? Well, we've seen a little bit of that already, and we talked about two ways you can handle it when alpha takes the value of 0.3. We've gone through it, hopefully you will see how it works. In general, there are at least a couple of ways you can do this. One way is to distribute the power. If we have an object that takes a value of 1 over x raised to the power of alpha, what we can do is that we can rewrite it as x raised to the power of minus 1 raised to the power of alpha, which is just x to the power of minus alpha. And by a similar token, we can take it apart and assemble it in a different order. Instead of writing it as x to the power of minus 1 raised to the power of alpha, we can first raise x to the power of alpha and then raise to the power of minus 1. They're all equivalent. So how is that relevant to us? Well, we effectively have an expression that is something like 1 over q1 over q2 raised to the power of alpha. If you stare at this expression hard enough and start to be able to treat q1 over q2 as the entire bundle of x, now we can just rewrite it as q1 over q2 raised to the power of minus 1, then raised to the power of alpha. Or we can rewrite this as q1 over q2 raised to the power of minus alpha. Or we can write this as q1 over q2 raised to the power of alpha and then raised to the power of minus 1. It doesn't really matter which way you prefer. But there is a particularly convenient expression we can take advantage of in this particular instance, and that is coming from this expression. We can in fact process the inside part of the power first, and that would give us q2 over q1 to the power of alpha. And that's exactly what we're showing on the right hand side of this expression. Because by flipping this ratio upside down using the minus power, what allows us to do is that now we in fact have exactly the same expression q2 over q1, but raised to different powers. And coincidentally, again, their powers will add up to 1. So then you can collect these two terms and they just become q2 over q1, a much nicer expression. Well, of course, you can follow exactly the same method we used on the previous slide. So instead of using the flipping the ratio type of approach, we could simply plug in these expressions into the following expression of marginal rate of substitution. And then what we'd have is just MRS is equal to minus alpha raised to the times q1 to the power of alpha minus 1 times q2 to the power of 1 minus alpha divided by 1 minus alpha times q1 to the power of alpha and q2 to the power of minus alpha. And now, to work with this expression, we need to recognize that, first of all, the value of alpha minus 1 is in fact negative, because alpha is between 0 and 1. So subtract that by 1, it's going to lead us to the negative territory. And similarly, the power here is negative, because alpha, again, is between 0 and 1, so the negative of that is going to be negative. So what we're going to do is just going to take advantage of negative properties on the power. I'm going to write this in the most decomposed format. We're going to have minus alpha over 1 minus alpha, which is just a ratio of our constants, multiplied by these dizzying terms of q1 and q2. I'm going to process them separately, because perhaps that's easier to think about. So we're going to have q1 to the power of alpha minus 1 times q2 to the power of 1 minus alpha times 1 over q1 to the power of alpha times 1 over q2 to the power of minus alpha. And now we're going to try to figure out a way to get rid of negative powers and flip them into positives. And by doing that, we will be able to hopefully collect these terms of q1 and q2. So what you would realize, hopefully, is that q1 over the power of alpha minus 1 is just 1 over q1 to the power of 1 minus alpha. And similarly, 1 over q2 to the power of minus alpha is simply q2 to the power of alpha. Now we can rewrite the entire expression as minus alpha over 1 minus alpha times 1 over q1 to the power of 1 minus alpha multiplied by, let's switch these two terms. I can put q1 and q1 together. We're going to have 1 over q1 alpha times q2 to the power of 1 minus alpha, and then multiply by q2 to the power of alpha. Again, you have the expression because we're switching the positions of these two expressions. Now with these expressions, I can collect q1 on the bottom and q2 on the top. I would have minus alpha over 1 minus alpha times 1 over q1 to the power of 1 minus alpha times q1 to the power of alpha. And then q2's are all on top of this ratio. So I'm going to have times q2 of 1 minus alpha times q2 to the power of alpha. And now, hopefully you're able to see that we can collect the terms of q1 and q2, and we will have exactly the result we have at the end of this expression. Again, as I said, this algebra is necessary and helpful, but it is not economics. So don't be too worried about how you get to the end, as long as you know one way that you're most comfortable with. Now, back to economics. We have now calculated that the marginal rate of substitution for any Cobb-Douglas utility function with the general parameter of alpha will take the form that looks strikingly simple, which is just the ratio of the parameters alpha over 1 minus alpha, the respective powers on q1 and q2 in the utility function, multiplied by the ratio of q2 over q1. And then, of course, remember there is a negative sign. Now let's try to observe this expression a little bit and make some interpretations out of it. First of all, we would notice that the sign of the marginal rate of substitution is negative. Why is that? Well, alpha is a positive number between 0 and 1, and therefore both alpha and 1 minus alpha are between 0 and 1, both positive. So the ratio must be positive. And again, because q1 and q2 are simply quantities of consumption bundle, they're going to be positive. So the ratio of q2 over q1 is positive. And then you multiply a positive expression by minus 1, the entire expression is going to become negative. Now think back to the interpretation of marginal rate of substitution. It is a measure of the slope of an indifference curve, which we said is downward sloping. And of course, its slope is going to be negative. And that's exactly what we have here in this expression. And you see that it does not matter what kind of consumption bundle we're thinking about, which means that regardless of any Q1 and Q2 combination you have in mind, the MRS is going to be negative. And second of all, this is completely general for any Cobb-Douglas utility function. It doesn't matter what kind of alpha you have and what kind of bundle you have for Q1 and Q2, the slope of the indifference curve is always negative. A second observation we would make about this expression is that the marginal rate of substitution is increasing in Q1 and decreasing in Q2. Let's think about the property that it is increasing in Q1. When Q1 is very small, this expression without the negative sign is very, very large because we're dividing a finite amount by a number that is very close to zero. And then you put on a negative sign on it, it's going to be very close to negative infinity. So what's the interpretation of a negative infinity MRS? Well, think back to our story about sliding down an indifference curve. The magnitude of MRS helps us measure the amount of good 2 we need to take away from a particular consumption bundle when we throw in one extra unit of good 1 in order to keep the consumer indifferent. So when a consumer has almost no good 1, which is when Q1 is almost 0, and then you give this consumer one extra unit of good 1, how many units of good 2 can we take away from them? Well, it turns out that if this consumer's preferences can be represented by the Cobb-Douglas utility function, you can take away an almost infinite amount. Well, what's that interpretation? That is actually saying that this consumer values very strongly about the variety in the consumption choices. When the consumer has almost no good 1, and you offer this consumer the first piece of good 1, they're willing to give up a huge amount of good 2 in exchange for that variety coming from good 1. Now, if we look back to this expression, as the size of Q1 increases, absolute value of this expression becomes smaller and smaller and smaller because we're dividing a fixed amount by a bigger and bigger and bigger number. So the absolute values start to tend towards 0. Now, as the consumer has more and more and more of good 1, as Q1 increases, how many good 2 can we take away from them to keep them indifferent? Well, that amount we can take away becomes increasingly small. What it says is, as I have more and more and more and more of good 1, and as you take away more and more and more and more of good 2, I start to value good 2 more and more, and therefore it becomes increasingly difficult for you to replace good 2 with good 1. In other words, to take away the same amount of good 2, you will now have to give me a larger and larger and larger amount of good 1 to compensate for my loss of utility coming from the more scarce product in my consumption bundle. To see that, that's a very natural property that is already embedded in the indifference curve. The slope of the indifference curve is very steep when Q1 is low and Q2 is high. In that scenario, the consumer values Q1 a lot and Q2 by not so much. Of course, we're talking about these in the marginal sense. We're thinking about marginal utilities when you have a lot of Q2 and very few Q1. Now, if you try to offer this consumer one unit of good 1 to replace some amount of good 2, the consumer is willing to give up a lot of good 2 in exchange for that very rare unit of good 1. However, as you move down the indifference curve, now the consumer becomes very rich in good 1, but very poor in good 2. Now, if you keep offering the same extra amount of good 1 to this consumer, they're less and less and less willing to exchange it using a certain amount of good 2. In particular, the slope of the indifference curve now becomes very flat, which says when you increase good 1 by 1 unit, the amount of good 2 you can replace is now becoming really small. And again, this just speaks to the consumer's preference towards variety in the opposite direction. Overall, it turns out that this type of particular shape of an indifference curve embeds a preference property that the consumer prefers variety. Although you are able to substitute one good with the other to some extent. And this property turns out to be general in many utility functions. And in fact, it is a very desirable property because we think it captures many realistic features of people's preferences in reality. And this property is generally called the diminishing marginal rate of substitution. And again, the intuition is simply that it becomes increasingly difficult to give up things that we have very little of. If we look at a numerical example of a very particular Cobb-Douglas utility function, these numerical values shows the marginal rate of substitution along the same indifference curve. And what you see is that the values keeps decreasing in its absolute value because it's becoming increasingly difficult to replace good 2 by good 1 as we slide down the indifference curve.